All right. Looks like people are coming in, and so yeah, let's get started. So, thanks everyone for coming to lecture 7 of CS 545, the Introduction to Robotics course. So today we will be covering Kalman filters. So some logistical information. So lab 1 is due February 4th. So hopefully everyone should have a team by now. And we just posted some messages on Piazza to describe instructions on how to submit the lab and so on. So just take a look at Piazza for that. And homework 2 is out. So hopefully that's going very well. I'm guessing most of you wait a few days before starting it anyway, but it's ready in case you want to get a head start. And then yeah, submit on Gradescope as usual. I'll get the Gradescope submission set up. And yeah, so I have the Google Doc link open if you want to type in your question. Otherwise, if anyone does have any questions, let me know. And hopefully more people will come. I mean, I do record it, but ideally it's like the backup option. Yeah, any question? All right, so let's get into the technical portion for the lecture. So let's just do a very quick review of what we've covered the last few classes. So we made an assumption that we are following a certain Bayes mesh structure. So we have a Bayesian network that characterizes the evolution of control, the state, and the measurement. So we call that U, X, and Z. Again, sometimes you might see control as action, so it's like A instead of U, but it's basically the same thing. And we make these assumptions that simplify our conditional independence assumption. Oh, why is there a video of me over there? Well, hopefully it's not blocking the core of the slide. Well, anyway. All right, so we made an assumption about stationary dynamics. So again, dynamics means we have some state, so state of the world, some action that the robot took, and then we have to characterize what is the distribution of all the next possible state. And it's stationary because we're making the assumption, well here, I guess technically speaking, I should have written that, we're going to make this the same for all values of t. So for all values of t, we get something like this, where we also have like the Markov assumption so that we can get rid of a lot of the conditional independence assumption. And then yeah, that's what the Markov assumption means as well for the dynamics as well as for the measurement probability. So probability of ZT conditioned on essentially all the stuff that came before it. You just have to condition on XT. So you can kind of see that from the structure of the Bayes net where the only parent of ZT is XT. And we did cover it last time, but there was a question about does UT happen at XT minus 1 or XT? So notationally, it might be a little bit confusing, but UT is what makes the system go from XT minus 1 to XT. So think of UT as happening before XT, if that intuition makes sense. And last class, we also talked a lot about belief. So you remember what those were? So these are things that represent a robot's internal knowledge about the environment state. So again, if you differentiate it from the true state, which in practice we don't know exactly, but we have some probability distribution about that true state, which is what the robot can use for its algorithm or whatever. Yeah. And what beliefs do is, if you remember from last classes, we have some kind of distribution over all the possible states that could happen. So if you imagine like a discrete set of states, like there's two possible states, the door is open or the door is closed. And then a belief is a distribution, so you have to assign some kind of probability to either the door is open or the door is closed. Yeah. And more precisely, it's also a posterior probability where you have to condition it on your measurement observation. So like if you're at time t, you would have to incorporate the measurement update at zt, and then you get your belief about xt. Yeah. And yeah, mathematically, we would write it like this. So the belief of xt is the probability of xt conditioned on the 1 to t, so all the prior measurement and all the prior action. And we also talked about the belief with that bar above. So the prediction of what is your true state, xt, but before you actually incorporate the measurement. Yeah. So that's why you go from v1 to t to, no, t minus 1 here. Yeah. And then last class, we also talked about Bayes filters. So this is a general algorithm for computing beliefs. So last slide, we talked about, what are beliefs? But then we need some kind of algorithm to compute that. And this is the way that it looks like. It's just 6 lines long. And some of them are like, for all and for. So, those aren't really lines. So, yeah. But this is also not, it's also a little bit tricky because it's not really showing every single possible step. It's really only showing one time step. So you have your Bayes filter with the variable as input, and they have t as their subscript or t minus 1. Yeah. So whenever you see something like that, you should think that it's like a kind of recursive algorithm. So the decision or the computation of belief at time t for state xt is going to depend on the belief that we computed from the last time step, plus anything new that happened after that. So this is all the new stuff, the action that the robot took, and then what we observed from it. So again, think of ZT as like coming from your sensor, maybe a GPS sensor or some kind of camera image that gives you information. Yeah. And I think we talked a lot about line 3 and 4. That's basically the only thing to talk about here. And I think we went through the derivation here, so hopefully you all saw how to compute this. So we did it for the sum, but the integral is like basically the same. Like every time you see a sum or an integral, just think of discrete and continuous. Yeah. And everyone remembers what the eta means here. It's like ETA. That's a Greek symbol. It's not like estimated time to arrive. So this thing, which is like some kind of constant that makes it a probability distribution. Yeah. So the recursive algorithm, which here we're just showing like one time step. So everyone remembers does everyone remember like roughly why this is the bad algorithm? We went through the derivation, but usually when we talk about algorithm, if we talk about the simplest one, then that means we don't make many assumptions, but then that also means, well, it has to be very general. Maybe there's some like drawback to it. If we make more assumptions, maybe we get like better performance under those assumptions. So that's a general principle in robotics that I think about. Yeah. So no, the general issue is that this algorithm is really intractable. So you really need a very simple robotics problem. Like we talked about that strange looking robot that was looking at the door and it can push and it can do nothing. And all we had to do was say the door closed or open. And that's kind of that's like a toy example. The only reason why we talk about it is just to give you an example of how to go through the math. like in practice, you would probably like hope you would be working with more interesting robots. So, yeah. So the motivation for what we're studying today is that Bayes filters are generally impractical. Like you can run them, but they would take like a super long time to compute. So the Gaussian filters are like a variant of Bayes filters that make an assumption here that you can represent belief with multivariate normal distribution. So hopefully you'll see in today's lecture why we went through all that trouble of defining here's what a multivariate Gaussian means, here's like how you write out the density function. Uh, Everyone memorizes the density by now, hopefully. Yeah. And the variant that we'll cover are the Kalman filter and the extended Kalman filter. The other two, no, they're interesting, but I don't think we have time to cover, so they're in the book. So you can look at them at like after this class. Any questions up to here, like the motivation or yeah. So is your question, why are we calling this a filtering algorithm? Like, you mean like the literal word filtering? Or well, we have to put a name here somehow. So I think, I mean, so the term filtering is like kind of like you have many things and you have to filter things so that you only pick a subset of those. So my intuition for the wording filter is that you have all your possible states that the robot could be in or the world could be in. And only a few of them are like highly probable. And so in sometimes we're like filtering for just those states. I mean, sure, the robot could be in any possible configuration, but no, some of them are much less likely than others. So, yeah. Other question? Yeah. So why it's called filtering? Because you get rid of noise. Yeah, I got that. You could argue that. Yeah. And also, like, you have to put a word there. Like, if you don't have filter, it's just Gaussian, and Gaussian is like super broad, and we have to be more specific when we talk about Gaussian. So, yeah. All right. So what are the assumptions we're making? So, if we make assumption, then maybe our model will do very well if those assumptions are satisfied. If they're not, then we have to rethink our approach. But for today, we're going to assume that we'll work with some robots and states of the world that follow some Gaussian assumption. And because we're working with Gaussian, so if you remember, Gaussians are only for continuous random variables. You can't really have a discrete random variable, then you model it as a Gaussian. It doesn't make sense to do that. So we're going to assume that the states are like in continuous land. So maybe the state is like, where's the position of the robot in a real line? Like in maybe a corridor where it can like take in any value in like meters or whatever. And we also assume that the dynamics model is linear in its argument. So remember that the dynamics model, it takes in X and U. So it takes in the prior state and the action to determine what's the distribution of the next state. Yeah. And so here's how we're going to write it out. So xt here. Xt is our state at time t. So maybe position of where the robot is. Xt minus 1 is the prior state. And then ut is the action that the robot took. And if you want to write it out a little bit more precise or mathematically, just think of xt as some state vector. So remember normally that when we write vector, they're usually they're column vectors by default. So it should look like that. Now the notation is, so here, because I've already used t here, I had to keep the t here, but then I added in 1 comma t, 2 comma t. That's just the component of this vector. So, and it has n dimensions. So think of an n-dimensional state. Then we have u be some kind of control vector, some kind of action vector. Yeah, it could be a scalar, but in general, it could be a vector as well. Now, in general, we don't need, so if you look at this, we don't need n and m to be the same. They can be different. Yeah. And so just a quick question, like what do you think, for example, epsilon here? Like what is epsilon? You've seen this before, right? Hmm. Yeah, so epsilon is a Gaussian random variable or multivariate Gaussian random variable. So whenever you see epsilon, that will often mean some kind of noise thing. I know in some other classes it might be like, an epsilon, like a small constant that you use in math, but for today we'll just view it as some kind of noise vector. Yeah. And do you see why like the matrix dimension, they all make the math work out? So your you have your A here. So A is a square matrix because suppose that you have no noise and then your control is like nothing. So it's like all zero. And you kind of have to make sure that A has the dimension to work out to make xt minus 1 go to xt. And A is like how the state transition if there's no noise and there's like no control. And then B is this matrix that maps from the control into a term that you just add to the other vector. Yeah. And R is the covariance matrix of the noise here. So quick question, why do we call this linear here? So like sometimes it's easier to think of linear and if you have like one variable, but here we have like n variables. So why is this linear? Yeah. So yeah, I think what you're getting at is it's linear in like each component of the x's, and then you get some linear combination when you do the matrix algebra, but it still again it's like a linear combination. So every component in x is just multiplied by some constant in some sense. So it would not be linear if we had something like, say, xt minus 1 transpose a xt minus 1. Because then you have like two terms together, then you're squaring things if that's intuitive. So this is why we call it linear in x and u. Yeah. But again, this is an assumption that we are making for today. If you're modeling something like a robot in your own domain and you see that you have good reason to believe that this is not what's happening, then you should not make this assumption. But we're making this assumption here that we have a linear dynamics model with Gaussian noise. All right. And when we make these assumptions, though, maybe let's just think about how would you write the state transition probability? So you have P of xt given ut and xt minus 1. So maybe take a couple of seconds to think about like how would you write out this term in bold? This will be something that we'll ask you to do a lot. So it's a good exercise to make sure that you're familiar with writing out this term. So, Yeah, I would check the Google Doc, but it's gonna be a little bit difficult to type in. So you might just want to just do like handwrite it or use your iPad or whatever to, uh, yeah. Or you can do it in your head too if you want. Yeah. Hmm. All right. So did everyone get it? All right. So let's go through this. So if you have to write this out, then we can start from the definition of the multivariate density function. That's this thing here with mean vector mu and the covariance. This is the sigma inverse here. Now, if you look at xt, then xt is this thing. It's the a xt minus 1 plus b ut. So that is like the mean. That's the mean, right? So you just take this thing and you plug it in for mu. Because the only thing that this is, it's like this is like the mean, and then you get zero mean noise added on top of that. And because this noise has covariance matrix R, then you would have to plug in, well, R inverse here. So this is how it looks like. You keep whatever normalizing constant you have, and then you have the exponential function with the mean vector here, and then the inverse covariance there. Yeah. So hopefully that's clear how to derive it. All right, so we talked about the dynamics model, but the other assumption that we make when we're talking about the Gaussian filter is that we also assume the measurement probability or the sensor probability is also linear in its argument with Gaussian noise. So that means you should see some matrix times something plus some noise. And then that's what we have here. So we have some kind of measurement vector. So again, maybe it comes from like a GPS signal that you query, then it gives you a vector of all the relevant information. C is some kind of matrix that maps from the real state to your observation. And then you get this as the extra noise that you add. And if all right, so if you're also wondering where C comes from and where the other matrices come from, well, two things. So either we'll just give it to you, so you don't have to worry about where it came from, or you have to like somehow compute it yourself, and then you would like put it in your model. So it does assume that you have some way of getting this matrix. For this class, I think we'll mostly just be giving it to you. No. Yeah. So similar question, what's the measurement probability? So if you just think like 10 seconds, think about how you would write it out. Uh, Everyone got it? Hmm. Not much reaction today. Interesting. So here's how it looks like. you have probability of VT given XT. You have the normalizing constant here. So again, it's kind of annoying to write it out, but you need to have it there to be mathematically correct. And you have the exponential function with the -1/2. And then you have z, which is the variable that we care about. And then we have to substitute like the mean vector with whatever this is. Because ZT is the same as this plus zero mean noise. Like if this term here, if the term does not have zero mean noise, then we would have to adjust and take that into account. But usually with Gaussian filters, we assume zero mean noise. Because like if we're trying to track some position of a straight moving device, then we might make the assumption that its position is going to be like the mean of the last position plus some zero mean noise centered at that position. So, I mean, in real life, a lot of things are not, well, actually, most things are not exactly Gaussian in real life, but Gaussians are also a very common approximation of various natural phenomena. Yeah, did you have a question?
That term on the right side, that whole Gaussian equation, that's the same as writing and yes.
It's the thing. So this, so when you're talking about this whole term when you write it out, it's the same as what?
It's the same as n parentheses CXT for the mean, comma Q for the variance.
Oh, okay. I gotta erase what. Where is it? And so you talk about something like this.
Yeah.
Well, so the distinction is that when we write stuff like that, this is just saying that random variable is drawn according to this distribution with density function expressed like that. So this is like a way of describing a Gaussian distribution, but but we would use this to refer to like the exact density function of this distribution. So they're kind of the same, but we don't really say it like that. Yeah. It's just the way that we talk about probability convention. Fine. So the third assumption that we have to make for Gaussian filters is that the initial belief is also Gaussian. So because it's a recursive algorithm, we talked about things like updates at time t, but we really need some kind of thing at time 0 to get things started. And that's where this comes in. So it's kind of annoying, but it's another thing that you have to watch out for when you're like writing code. You need to initialize it correctly. Yeah. So that's where this comes in. And we're using B, but it really should be belief here, like BEL, but yeah, it's the initial state. And then the other annoying thing is that we kind of need a separate covariance matrix for the initial time step. So you get sigma of 0, which is the covariance matrix at time t, and your mean at time t at time 0. All right, so for the next few slides, let's just go through some more of the calculation with how information is propagated. So what we're covering here is assuming that we know that the next update from the equation we just described lead to the next belief being Gaussian, then what are the mean and the covariance of that? So we're going to calculate the next mean and the next covariance, but we make the assumption that we are showing that, we make the assumption that, it's gonna still be a Gaussian. So strictly speaking, you have to do some more math to make sure that it is following a Gaussian by showing that it obeys like an exponential function that you can express in terms and rewrite the matrices there in terms of your standard mean and covariance. So if you want to see that, you can look at the textbook. It's about like 9 pages of matrix algebra. So you can check that, but we're going to make a simpler calculation here and assume that we know everything's going to be a Gaussian. What are the next mean and covariance matrix going to be? Yeah. Yeah, so if we think about what is the next mean going to be, then if you remember what this is, this was the dynamics that took in your xt and then gave us u, and then took ut plus 1 and then gave us the next state. So when we take an expectation of that, then we effectively get like what is the mean of your next state, right? Yeah. And if you do the math here, then hopefully you've seen that, this previous equation is linearity of expectation. You can always do that even if your random variables are dependent on each other. What do you do now? So I'll tell you this. So when I work with fiddling around with expectation, every time I see a constant inside one of those E terms, like I pull it out. Okay. So because the issue with that, it just doesn't really make sense to have a constant inside an expectation. So the expectation inside should be a random variable. So you pull out matrix A, you pull it out here, you pull out this thing. So ut plus 1 is considered like a constant because it's like something well, it is considered a constant here because what we care about is like the expectation of the next state. So it's really the xt that we care about. And like ut plus 1 is like something that we know exactly. So the robot did something. Yeah. So what do we do now? Like what is this last term? Yeah. Yeah, exactly. So if 0 here, then well, you can also change the expectation of xt to be mu t. Yeah. So don't get confused. Mu t, not ut. Yeah. All right. So that was the next mean. So what is the next covariance going to be? So usually when we work with covariances and matrices, it's going to take more algebra to do. So we'll try to do a little bit slowly here. And everyone remember the definition of covariance, right? If you have the random variable that we care about minus your mean vector really. And then you do an outer product here. So like you have your column vector, then your row vector. So like if you visualize it like a big column with a line and with a horizontal line. Yeah. And then you get this thing. Now the xt minus mu t, that thing, if you remember from the prior slide, we can express it like this. Yeah. And what we did here is we substituted this thing here. So it's mu t. So if you remember the mu t plus 1, it's a mu t plus B ut plus 1. So the same thing happened here. Except we went from t plus 1 to t. So and it simplifies to this term. Right? So what we can do now is, if we have this term, then we can plug in your term here and then put it inside the expectation. And then this is the vector that we're taking the covariance of. All right, question. This is just like standard matrix algebra, so yeah, hopefully it's not too bad. I always feel like the issue is not like the algebra itself is not too bad. It's just like thinking how to get to this point is usually the harder thing. Like, how do you actually know that you're supposed to do this first? So, yeah, so we have our covariance matrix from time t. We have this thing. And then here we're just expanding and by putting in this thing here. So when we have this, what do we do next? Like, what's the next thing? What's the next thing we could do when we see this? Yeah. I mean, I would look at the Google Doc, but it's also very hard to type in. I think when I asked you, like, what do you do with this algebra here? Yeah. Yeah. What? Multiply each term. Well, so what do you? So really, if you have like a term like a plus b multiplied by a plus b transpose, you can multiply for every term in the first parentheses, you multiply it with every term in the second parenthesis. So it's roughly like that, yeah. And then you sum everything up. So standard algebra, except you have to watch out for the transpose there, because the transpose means you have to be very nuanced and track, like, is this thing like a column vector or a row vector? So like there's some like math equation that you can't you have to make sure that the dimension work out. So what we did in the third line is we took this transpose and then if you remember, you can apply the transpose for each individual term. So like the transpose here goes to the epsilon transpose, and then the transpose goes to here, but remember that it flips the ordering, right? So if you have but it's like if you have two matrices, then the transpose is like you can transpose both of them if you flip. Yeah. So and then here we do some algebra. Yeah. And then when I do this, the main thing that I always check is, again, to make sure that all the dimensions work out. So every single term here, like if you split it up into like, this term plus this term plus this term, they all better have the same dimension, like the same number of rows and columns, sigma t. Because otherwise, if it doesn't, then it's not like valid matrix algebra. Yeah. Oh yeah. What's next? Oh yeah. So we have an expectation with a bunch of terms inside that are summed up. So you just apply linearity of expectation, and then you get expectation of this term plus expectation of this term plus expectation of this term plus expectation of this term. Yeah. and just barely fit in the slide. So, yeah. What's next? Yeah, so hopefully everyone's comfortable, like, at least following this. So, we might ask you to go through some matrix algebra too. So here's what we're gonna do next. So we're gonna do a number of things. So we're going to pull out some constants outside the expectation. So if you look at the first one, we have an expectation of some matrix multiplication here. But because A is a constant, it's like a constant, then it doesn't vary, so you can pull it out. And like the expectation that we care about is with X here. And so you can still pull out the constant like this, even with your matrix multiplication. Yeah, and if you look inside, like what's over here, you get xt minus 1 minus mu t minus 1, and then the same thing transpose, which means you get sigma of t minus 1, because that's literally the definition of what a covariance matrix means. Yeah. And then for let's skip to the last term. So the last term is expectation of this outer product, which has your column vector times a row vector. So it turns into like a matrix, a square one actually, because, well, the covariance matrix is square, so this thing better be square as well. And also because you have the same vector, so it's like n by 1 times 1 by n, so it's n by n. And we make the assumption that we've been using R to indicate this is the covariance matrix. And it's also zero mean, so that way when you write out the definition of the covariance, you get zero here. Like you get yeah. So that term becomes zero, then you get exactly what this is. Or and the last thing that we're going to make use of our assumption about essentially noise being uncorrelated with other information. So again, this is an assumption that we're making for the model, and how well the Gaussian filter will work, depends on how well the scenario will naturally follow these assumptions. And so with this, remember that we can pull out the A, and then we get xt minus 1 minus mu t minus 1 times epsilon transpose. Then if it's uncorrelated, if it's uncorrelated, you can pull it out. Like I think you had that in one of your homework questions. So hopefully that looks a little bit familiar. And you can do the same thing here. Then whenever you have a zero vector and then you multiply it with another vector, it turns into zero here. Yeah. I think there's a very slight typo. I think there should be there's a missing transpose here, but that just makes the matrix algebra work out. So yeah. Any questions about this? So, yeah. So, uh, so this is the definition of the covariance, where the all right, this is zero mean. So normally the covariance, when we write it out, it's like if this thing here, you have your random variable minus a mean vector. Yeah. But we make the assumption that epsilon is distributed with zero mean. And then the R is just like the notation that we were using earlier. It's this thing. Yeah, right here. So here I just put it as R. So here in the math there you saw RT, so that means that it varies according to time t. Here I just made the assumption that it doesn't vary yet. So it's like stationary noise. But again, if you think for your own domain that the noise is not stationary, then you should have a t there, like RT. Yeah. All right, so that brings us to the Kalman filter finally. So putting it all together, if you recall the math that we were just doing, we have derived the next mean and the next covariance as follows. So mu t is equal to a times mu t minus 1 plus b times ut. And then sigma t is a times sigma t minus 1 times a transpose plus r. And if you write it out, like the book shows it like this, where you have your Kalman filter. So here they put t under every matrix, so it's time varying. If you think you're modeling something which is stationary, then you can get rid of some of the t in the notation. And if you look at this, it's kind of similar to the Bayes filter, except there's Gaussian. So if we represent our belief with Gaussian, then it's enough to just predict what is the next mean and what's the next covariance. Because those two pieces of information, that's all you need to specify a Gaussian distribution. Yeah. Like I don't need any more information from you to like write out what is the density function if you give me the mean and the covariance. So that's why this algorithm, the whole point is to take in your prior belief and then you return your updated belief. Yeah. So instead of BEL, we just have these two terms. Yeah. And to be precise, what we've really done is we've shown like the line 2 and 3. So it's like the next mean and the next covariance. Now, the reason for this is that we have to take into account the measurement noise. So the computation that we did before, that was based on the dynamics, right? So it's based on the dynamics and then the noise from that. But we didn't consider things like what's the measurement noise. And that's where this thing comes. So yeah, we're not going to do the derivation. You can look at that in your book. Again, it involved more like matrix algebra, like maybe I don't think it's like 8 or 9 pages, maybe like 2 or 3 pages. Yeah, and if you're reading books about the Kalman filter, like you'll often see references to the Kalman gain. So that's the specific term that's used for this thing. So no, essentially, I think what happened is that when people did the math for the Kalman filter, they found that if you express things as KT, then that leads to like some very nice matrix algebra. Like you can actually write things in a much simpler way than if you didn't have that. Like if it has a whole bunch of terms here, and then it also makes it easy to describe and analyze the system as well. So if you want to talk about like what's the measurement noise? So remember that QT is that noise that came from the measurement, like it was this term plus this zero mean thing with covariance Q or QT. Yeah. And so I think whenever I look at the math behind some matrices, like it helps to think about what happens if your noise is like at different extremes. So if you have no noise, then this QT will just be a bunch of zeros. So you can have the covariance be like 0, for example, like in every component. And then you basically get this thing. And if the entries in the covariance matrix like go to infinity, then that term dominates, and then the subsequent calculation, they end up like essentially spreading out the covariance to indicate that no, the system doesn't really have much confidence about like where the mean is. So hopefully that intuition is kind of clear. Yeah, so again, if it seems a little bit confusing to look at all these terms, the way to think about it is look at the base filter and then just replace the belief with mu and sigma. Because like that's basically what's happening. Any questions on this? So yeah.
Make a much more clarification on life.
So which line are we talking about? Oh, line 4. Oh, well, so up to now, we were only really talking about line 2 and 3. Right? So line 4, 5, and 6 are like just other math that you have to do to take into account the noise from the sensors. So if you remember with base filters, we have the distinction between the belief with the bar, which was just taking in the transition dynamics, and then you take in your sensor noise. And so a similar split is happening here. I didn't include a derivation of 4, 5, and 6 because I thought, you didn't want to see too much more matrix algebra. Again, it's in the book if you want to read it. But so just think of this as like a matrix that you use in your subsequent calculation. So I think in the book, if you look at the algebra, they do the algebra, then they assign like these matrices will be assigned to KT. And then it makes the rest of the math a little bit more simpler notationally too. Anyway, I think this is a good time to take a short break, like a short like 5 or 6 minute break. So if you want to look at this a little more, you can do that. And otherwise, yeah, have a good short break.